Okay, I saw that last night on the freeway. It was too good to pass up. And so I've decided to put it in the PowerPoint because we're talking about momentum. Momentum facts, what does it mean? Momentum's equation is that. Okay, why they use P, I have no idea. But momentum is equal to the mass times velocity. Okay, the P is probably because, could we use another M? If we said M is equal to mv, that'd be too confusing. And so they chose something else. One of the things you need to know is that momentum is a vector. It has direction. It has a magnitude and direction. Excuse me? Okay. Now, if I am moving in a certain direction, I have a velocity. That is the direction of my momentum. Momentum and velocity of the object are always in the same direction. The units. Remember how when we were talking about force, the units for force were in newtons? There isn't a special name here. The units are kilogram meters per second. Why? What are the units for mass? Kilograms. And what are the units for velocity? That's why. Okay? Momentum is conserved. We'll talk about that tomorrow. That just means that if we're having a collision, the system of the two things colliding has to be, the total of it has to be the same before and after the collision. If you have an object that is moving or sitting still, you require a force to change it. Just like when we were talking about wanting to accelerate something. To accelerate something, you need a force. Here, you need a force to change something's momentum. You need a force to change something's momentum. Momentum means that if you've got something moving or sitting still, it's going to keep on doing what it's already doing. Does that sound familiar? Okay, if I take this shot put it on the ground, and start pushing it, I'm going to have to apply a force to get it to change direction, to speed up, to slow down. To change its momentum, I have to apply a force to it. And the force I apply is in the opposite direction of the momentum. Questions? This one's the interesting one. It's possible, you remember when we were talking about the bug hitting the front of the semi? It's completely possible that that bug could have the same momentum as the semi. Wow, that sounds like a good premise for a movie. Like Ant-Man or Wasp-Man? Or is it Wasp-Woman? The Wasp. Sorry. But is it possible? The technology is not here today. But if we go back 200 years in time, and you looked up in the sky and saw this great big huge silver thing going overhead, would you have freaked out? Because the technology for airplanes was not in existence at that point in time. Don't know what you guys are going to come up with. Ant-Man may be possible. Don't know. It's up to you. So it's possible that something big and slow could have the same momentum as something small and fast. If we look here, this is the formula for momentum. We have P is equal to mass times velocity, where the mass is a scalar, and we multiply by velocity, which is a vector. So you can change something's momentum by changing its mass, by keeping the velocity constant, or keeping the mass constant and changing the velocity, both of which will change its momentum. Questions? I'm going to show you an illustration of that in the next slide. And on the next slide, you do not have to keep track of what it says, because it's basically just showing you what you see here. Bless you. If we look at the next picture, we have a car, a bus, and a train. It's hard to imagine that they could have the same momentum, but let's try to look at an example. If we take the car at 1,800 kilograms, like my Fiat, and have it going at 160 miles an hour, 80 meters per second, it'll have a certain momentum, and I will be screaming my head off, or at least my wife will. It will have that momentum. If, on the other hand, we take this bus, which has 9,000 kilograms going at about 30 to 40 miles an hour, 16 meters per second, it will have a momentum, the same momentum. Or if we take the train, do you see a tendency in the velocity? The train's going to have a huge mass. What's going to happen to its velocity? It's going to be fairly tiny. But it, again, has the same momentum. Again, you do not have to copy this down. This is just for illustration. And I have no idea why the plural of momentum is momenta. I don't speak Latin or Italian, but okay. There is a relationship between momentum and inertia. Inertia is basically how much is its mass. Which one has more inertia? 10 kilograms or 20 kilograms? 20 kilograms, of course. And that inertia is going to, more inertia it has, the more it's going to keep from doing something. It only depends on the mass. If we look at momentum, however, it's a moving mass. And therefore, the moving mass is going to want to resist change. Which one has more momentum? A 10 kilogram mass going at 40 meters per second, or a 20 kilogram mass going at 20 meters per second? $10 going at 40 meters per second, or a 20 going at 20 kilogram meters per second? 20 meters per second. Which one has more momentum, or are they the same? They're the same. Okay? So it depends on both the mass and the velocity. And again, momentum is a vector. Inertia just depends on its mass. It doesn't matter what direction it's going. Momentum depends on what direction it's going. If we have a ball, again, its momentum depends on the mass and velocity. In this case, we have a 1 kilogram mass A going at 1 meters per second versus a ball B, which is the same mass, but it has more velocity. It obviously has more momentum because 3 times 1 is more than 1 times 1. Questions? Therefore, if ball A is moving at 1 meter per second ball B is moving at 3 meters per second, just like what was said before. If we apply a 1 Newton force on each of one, trying to push them sideways, which one is going to be able to be deflected more? The one with less momentum. It's going to take less force to deflect it because it has less momentum. So how do we change something's speed? We use something called impulse. Impulse is basically force times time. Hold a second. Impulse is defined as that. And let me explain what that means. If we look at the definition of Newton's second law, remember that force is equal to mass times acceleration.
She has to leave right now.
Raquel. You're late. Remember, force is equal to mass times acceleration. But we defined acceleration as this, remember? Okay, you do not have to write this down. You're not going to have to prove this. I'm just proving to you what they mean. And this is what Newton went through. If we substitute this for here, we get this thing right here. Force is equal to mass times a change in velocity over time. If we subtract both sides by time, we get the definition of impulse. If we apply a force for a given amount of time, we're going to change its momentum. If we apply the force for a longer amount of time, we will get more change in the momentum. Any questions? So, let's think about this for a second. If you're in a car crash, your mass, your car, and you have a certain mass. You're going at a certain velocity. Do you want that velocity to change in a short amount of time, therefore have a huge force, or a large amount of time with a small force? Okay, let me give you an example. One of my friends from junior high went to a school in northern Minnesota. His sister bought a bar in southern Minnesota. And he was coming home for homecoming. It was this week. And when he was coming home, he was driving, and he had a 1956 Chevy. Beautiful car, remodeled, everything. It was fantastic. And but the problem was, it didn't have any seatbelts. It had no airbags. His sister was serving some guy at the bar, and he was going, "I want a tequila, please." And he downed it. And then 5 minutes later, he wanted another tequila. And about 15 minutes later, he wanted another tequila. And this went on through the evening. And about closing time, he went, "Ah," and left. And he traveled north towards his house. Problem is, he and Dwight met. They had a head-on collision. And Dwight, because there was no seatbelt, no airbag, was impaled on the steering wheel. He died instantly. About 4 years ago, however, my wife was in an accident with our Vega. The one I have out here is actually our second Vega, identical ones. But our first one, she was driving down Foothill. She was going the speed limit at 40 miles an hour. Someone was coming at her, a little bit less than the speed limit, about 35, but turned left right into her. Fortunately, in modern cars, you have a crumple zone. When that crumple zone crumples, it basically causes an airbag to get bigger. And when it gets bigger, you hit it, and it compresses down. It's like you're going into a balloon. Well, how does it get big so fast? Well, it's sort of like having some gunpowder on the steering wheel, and as soon as the front of the car starts crumpling, that gunpowder explodes. And it produces from that small amount a huge amount of air. My wife's only problem from this accident was she had some burn marks on her arms. Would you rather have a burn mark on your arm or a steering wheel impaled through your body? What? You'd rather be dead? Yeah. I don't think so. Okay, so let's get some extremes in here. In this case, the time that it took for this truck to stop was very, very short. Therefore, the force on the truck was very, very big. Likewise, in this one, where it ran into a bridge, would it take very long for it to stop? No. Therefore, there was not much left of the cab because of the huge amount of force. Likewise, car meets truck. Did it take much time for them to stop? No. On the other hand, something we have this truck stop. Basically what they are is a grade where as you go on it, you start going into it and there is an increasing depth of gravel and sand. So that when you start going on it here, there's a little friction. As you get here and here, your tires go deeper and deeper into it. And it slows you down, but it slows you down gradually. Do you guys know why we have one on Angeles Crest? Because about 10 years ago, there was a 18-wheeler going down the 2 freeway, and its brakes broke, and it ran over one person and ran through a bank. Bank, library, something, it destroyed that. Why? Because it was not able to stop. It took the entire building to stop it. Fortunately, we have these now. Now, on the other side, this is a guy named Clint Eastwood. He's a great director. Back in the 70s, 80s, 90s, he was an actor that played a role of Dirty Harry. Dirty Harry was a cop in San Francisco that got the job done but didn't always follow the rules. Okay, but before I go on, does anyone know how a bullet works? Yeah. Bullet has, basically, a bullet has in it some gunpowder. Okay, and out here is the bullet. Back here, in the very back, there's a firing pin. There's a firing place, a place where the firing pin from the gun hits. When it hits it, this place right here explodes. When it explodes, it takes all the gunpowder in here and it burns it. When it burns it, it becomes a gas. Now, on a gun, there's no place for that gas to go except out the end. Now, on the guns on the top, is able to apply a force, but it is only able to apply the force that far. On Dirty Harry's gun, it's able to apply it over a longer period of time. Therefore, if it's able to go over 3 times the distance, 3 times the time, what can you tell me about the velocity? It's going to be 3 times as fast. Yeah?
Is that why they use the rifles or something?
That's why in the military they use the rifles because they go faster. There's another interesting thing about this, and it has to do with the next topic. The next topic is angular momentum. In angular momentum, if I'm turning something like this wheel, if I take it like this, is it going to be easy for me to go like this? If it's just sitting here. If on the other hand, I go like this. Is it going to be easy for me to turn it? No. In fact, if I put it on the side, okay, why is it not working?
What the heck?
It's going to be able to go like that. It's not going to tip over. But guess what? They use them on cruise ships. How many of you have ever gone on a cruise ship? I have too. Now, how many of you have ever gone deep sea fishing or out in a boat in the Pacific? Have you been out there during a storm?
No.
I was out one time when we had 12-foot waves.
That's not safe.
And it wasn't good for my tummy either. Why? Because the boat went like this way, and but in a ship, what they have is basically this thing right here spinning, just like this, spinning, so you don't go back and forth this way, and you keep on going on a straight path. That way, what?
If you put that on the floor, it would just really straight.
I don't know. I don't want to try it right now. Now, you guys have seen, you guys do not have to write this down. Okay, just listen to what I'm saying. Angular momentum depends on a couple things. One is your shape. For example, if you're in a bike race, you have two types of wheels. One that is the normal ones you see, or there's another type that is solid, it's like a disc. This one right here has more inertia than the disc. Therefore, it's harder for it to get up to speed. But if it's harder to get up to speed, is it going to keep on going once it's up to speed? Which one would you want for a sprint? The one with very little rotational inertia, or one with a lot of rotational inertia? For a sprint, you don't want a lot of rotational inertia. You want to get up to speed for the 100-meter dash in the bike race very rapidly. But in the marathon, you want this type, the normal type of bicycle wheel. Why? Because it takes a longer for you to get up to speed, but once you're going, you're more likely to keep on going. You can take your hands off. Have any of you gone bicycle riding and taken your hands off? You do it when you're going fast, not when you're going slow, right? Because of rotational inertia. Now, what we see here, however, is another aspect of rotational inertia, momentum. Rotational inertia not only depends on your shape, but your radius. Have you ever seen an ice skater with their arms out like this? They have a certain angular momentum. If they pull their arms in, they have the same angular momentum. But because their radius is smaller, that means their rotational speed is higher. And that's why they spin very, very rapidly, because they pull their arms out, pull their arms in. Are there questions on that?